All right, so today we want to look at how linear programming came into the picture. We saw the graphical interpretation of efficiency and productivity assessment, but how did linear programming come into the whole picture? So it's like going back to the root. Before you can build models and extend it, you need to understand. Okay, so we're going to look at the mathematics behind it. And that means that your linear programming has to be sharp. We will consider dominance. We will understand dominance. We will understand mixed efficiency. And then we'll look at the general mathematical model. All right. So we know that we can assess the efficiency of a company, a DMU, a firm, using linear programming than graphical approach. Why? The graphical approach uses only one input and one output. The moment multiple inputs and multiple outputs come into the picture, the graphical approach is dead. You cannot properly use a hexagonal polyhedral to be able to explain it. So that one is good. It uses few inputs and outputs. But in real life, things are complex. So now we need to find a way of dealing with complex situations. But before we do that, we are going to look at convex combinations because the principle of convex combination will help you to understand the use of linear programming. Now, linear programming embedded in it, which you learned, embedded in linear programming is convexity assumption. What is convexity? Let's assume that we have a point, a data point, which is 4 and 6 and 6 and 8. If you try to draw this, okay, and this is X here, and then that is Y there. If you want to do 4, 6, 4, 6 might be 4 here, 6 there. Okay, so it's going to be a bit longer. 4 here, 6 there. But if you want to do 6, 8, okay, that will go up here, but then this one will go very high there. So here we have 4, 6, which is this one, the first one. Let's call it A here. And then the B becomes 6, 4. Because A is feasible and B is feasible, a linear combination of them is feasible, but you got to be sensible about what linear combination are you going to use. Because between these two, there are multiple, points, data points that exist between A and B. So how do we get a linear combination of that? Well, one thing we can do is to use a 50%. So the coordinates for A is 4 for the X. And the coordinate for the B for the X is also 6. We add the two together, we have a value of 10. We take 50% of that and share it. And so you can see that if there's a C, okay, C, 50% of the 10 is going to be what? 5. Okay. And then for the Y, the first Y is 6. And the second Y is 8. If you add them together, you get 14. And half of that is going to be 7. So a complete split between A and B is going to be at 7. It's easy to do that because any of them is possible. Now, that means that if I want to get C, I need to weight. I need to weight the coordinates of A and B. And the weight I need to attach to A and B is 0.5 each. So I weight each one of them 0.5. So C is the generation of C, which is a virtual DMU, a hypothetical DMU. This C is a linear combination, a perfect linear combination of A and B. C is not feasible. C is not feasible. It's a virtual, it's not real. It's feasible, but it's not real. But a linear combination of them makes it feasible. So a linear combination is where you can weight the input and weight the output, and the input and the output is what make up the DMU. So it means that you are weighting the DMU. You are attaching importance. So C is going to say that I came into the world with the help of A and B. This is a contribution of A towards my coming into the world. And this is a contribution of B towards my coming into the world. And in this very example, C is going to say that A contributed 50% towards my coming into the world, and B contributed 50% towards my coming into the world. Now, it's not always going to be 50%. So this is the principle of convex combination. It is very central to what we are going to be doing. Is that clear? Does that make sense? Jerry, yes, does that make sense?
Yes, Doc.
All right. So we are using 5 weights. The weight is referred to in our parlance as lambdas. And the sum of the weight, because the weight is 100%, so the sum of it is going to be 1. Okay. So in this very example of our data set, the lambda 1 up to lambda 5 should be 1. These are what we use to build that virtual DMU that I spoke about. So we are going to, I went to 2 steps. So the principle of, why is this thing not moving? The principle of convex combination says that if I have X, Y, that is feasible, is a feasible input-output correspondence. The word feasible input-output correspondence is a DMU. And if this is located within the production technology, okay, which is in our table, the PPS, then this is possible, is seeable, is real, is there, provided that something happens. The first thing is that the particular input, okay, say input 1, is greater than or equal to the weighted combination of all the inputs, including that very input of DME1. Now remember, I'm using the one here to refer to the first input, and I'm using the 2 to refer to the second input. So forget about the left-hand side and look at the right-hand side. So the right-hand side is taking the DMUs, weighting the input. So this is one of the input, which is a first input for DMU1. 2. The first input for DMU2 is 1, and then it goes on and on. If I add this input, I should get the overall input. If I add this input, I should get the overall input. But I'm not just adding, I'm weighting them before I add them. I'm attaching importance to them. So the weighted combination of the inputs will make up an input constraint. Now, if you could remember, find Yogo and find Choco. Okay, we have 40x1 plus 50x2. Then I think that for the labor constraint, do you guys remember the labor constraint? I think it's 3x1 plus, is it 2x2? Okay. Less than or equal to 40 hours. Do you remember something like that?
Not really, Prof.
No. It will be not really if you were not in that class. You were not in that class.
Look,
Is
I
it?
was.
So was that it? And then the milk constraint is 4x1 plus
I think
x,
3x2.
3x2, I think so, yeah. 3x2. And then it's less than or equal to 120 gallons. But then I've forgotten the first one. I think the first one is x.
Okay.
Because they can't all be 3.
Yeah.
I think the first one is x. But let me just assume that it is. Okay. Now pay attention. So this is labor constraint. Okay, just so you know, this is labor, and this is milk constraint for producing fine yogo and fine choco. Now, so you can see that here, what is the X? The X is the quantity of the fine yogo. X1 is the quantity of fine yogo, and X2 is the quantity of fine choco. And what you are doing is that you are weighting them, okay? Or you are attaching, there's a 1 value in front of the X1. So you're taking 1 hour of labor time to produce Fanyogo. 1 hour of labor time to produce Fanyogo. And then you're taking 2 hours of labor time to produce Fanchoco. So these are resources. So what you are doing is that you are picking the resources and weighting the resources. These are the weights, the X1 and the X2. They are the weights in linear programming balance. Okay. Now, the same thing, these ones, the lambdas are the weights. These are also the weights, okay, in the linear programming balance. Of course, when we're doing the linear program, we never mentioned that these are the weights, but they are the weights. And the goal is to find them. In fact, in linear programming, the X1 and the X2 are the decision variables. In other words, they are the ones you are going to find because you don't know. But we know that you are finding them because they are helping you to be able to determine the target or the objective. And in that very example, the objective is Z. So Z is equal to 40x1 plus 50x2. So this is objective function that you're maximizing. This is a profit of Farm Ghana Limited. And this objective here is like we are going to find our objective, which is the theta or the efficiency score. So I want you to have that mindset from here because we are translating that principle here. So you can see that I created a labor constraint. Labor is an input. It's an input. Then I created a milk constraint. Okay, so they are all resources. They are all resources. For this very example of linear programming, there were no output constraint. But here in data envelopment analysis, after you created the input X1 constraint and input X2 constraint, because you have multiple inputs and multiple outputs, you got to create output constraint. In fact, you may have output 1 constraint, output 2 constraint, and all of that. So I want you to see this right-hand side here as the technology. This is what makes up the technology. Forget about what is here. Everything you see here on the right-hand side is what make up what you might call the technology, the Y and the X space. Okay, and the idea is that this guy, if I pick any input, that input that I am picking should be equal to the one here. The one, it should be equal to means that it should be inside the space. Okay, it should be inside the space. But if it is bigger, it means that it is outside the PPS. And that is why we talk about inefficiency here. Okay. Now, when you look at this one, we use a less than. Of course, you can go here and swap this. You can say that all of this one rather should be less than or equal to the X1. It's the same thing. And so what that means is that the technology should be equal to or inside, okay, inside the X. But of course, when it is inside the X, that is going to be inefficiency. And then when it comes to the output, it's the same principle. So if I pick an output, okay, that output should be equal to the one on the frontier. But the moment the output, because have the frontier in mind, like the frontier is something like this for the output case, okay, let's assume it's like this. The output must be inside the frontier. If it is inside the frontier, it means that that guy is inefficient. If it is equal to the frontier, it means that that guy is on the frontier. And so in this case, you would want the output to be what? To be less than or equal to. Now, where less than means you're allowing inefficiency and equal to means you're allowing efficiency. And then, of course, because you are restricting the weight to be 100%, you got to ensure that convexity constraint, which is this. And like in linear programming, when you come here, you notice that we normally have x1, okay, comma x2 greater than or equal to 0, which is a non-negativity constraint. And they are the x's. So the same thing. The lambdas, which are the decision variables, are greater or equal to 0, which means it's a non-negativity constraint. Look, you got to be able to explain every element here and connect it with the usual linear programming. But we'll come back to that. Okay. So this is the production possibility set. So everything I said is here. What we are doing is that we are using the 5 weights. Okay. We are summing all of the weights to build any of the virtual DMUs. The first equation says that the input x1 from all the DMUs is the weighted sum of the input x1 for each DMU. And then the second one is the same thing. Now, the second equation means that if we let x2 be the weighted sum, so that x2 on the left-hand side is the weighted sum of the input x2 of each DMU. It's a virtual thing we're building. It's not real. And that virtual guy is created by a linear combination, a weighted linear combination of all the real guys. You remember the definition of convex combination here. The C was not actually there, but the A and B were there, and we were able to create the virtual C from a linear combination of A and B. Guys, are you with me?
Yes, Doc.
Yes, Doc.
If you don't understand it, you ask a question. Okay. And of course, the third equation, we know that it is a convexity constraint. Okay. In any one of them, the inefficiency is possible. That's why we have the inequality sign. I've explained this already. The fact that there is that inequality symbol, whether it's greater than or less than, because you don't want an input to be more than what it's supposed to be. Okay. You want an input so if I draw the input space, okay, if I draw the input space like this, and you have this, and you have this, and you have that as if you have an input here, that input is too much. For the input to be efficient, the input will have to be here on the frontier. So what this one is saying is that the input, when it is bigger than the frontier, then inefficiency happens. Like this guy. This guy here is bigger than the frontier. It's far away. So, and this is input case. Okay. Input case. So when you are bigger than the input you're supposed to use, it means you're using too many inputs. Whereas this one is saying that you are producing too less output. That is the output side. So we can now combine this and create an efficiency measure. So all the points to the PPF can be expressed as a linear combination of any of the other guys. Every point, if I pick any point in the PPF, I can create a linear combination of any of the DMUs. And I've already said that the symbols here, the inequality symbol, mean inefficiency is possible because the real input and output that make up the DMU can use more input. That is input levels in excess of the minimum required for the output. Or alternatively, they can secure lower output than the required. And that is what we call the free disposability of input and output, which we have explained a long time ago. So that symbol, that inequality symbol allows for free disposability of the input. So that is known as the monotonicity. So let me ask, what will it mean if the sign was just equal to? What would that mean? Godwell, what would that mean if the sign was just equal to and not
I think
greater?
it would suggest that there's no inefficiency, so there are no slacks.
Yeah, so what would that mean practically? What would that mean?
So practically, it means that the firm is on the frontier is efficient.
Yeah, so exactly. So what it means is that we are forcing the DMU to be efficient. Now, why would that be unreasonable, Albert? Why would that be unreasonable?
Because not every firm is able to use the same combination of inputs to generate the same output.
Make it simple. What would that mean?
So let's say using the fan yogo, fan choco example, like labor and let's say capital example. It might not be possible for, let's say, Jerry's company to use, let's say, one labor and one capital to produce two fan choco, whilst I will use one labor and one fan choco to produce one. So naturally, we might have differences. So forcing us might mean that the model will not work the way it's supposed to work.
Okay. You've explained the thing so much that I'm even confused. Who can make it simple? Emily, how do you make it simple?
Okay, so okay, so I think the reason why we can't make let it be an equality is because inefficiency is possible. Like firms using more than they are supposed to, more inputs than they are supposed to, or producing less outputs than they are supposed to. It's possible for that to okay, so it cannot be an equality.
Okay. All right. You all understand what you're saying, so that's fine. So that would simply mean that if it is equal to, then the DMU is efficient. Okay. And of course, you are forcing them to be efficient. Okay, so now you want to assess the technical efficiency of a particular DMU. Let's say DMU 4. How would you write the mathematical formulation and explain it in a linear programming parlance for someone who does not know what DEA is about to understand? Because a person has done linear programming. This is what we are going to do. So we're going to assess the efficiency of DME4. Okay. Remember the data set. This is a data set. You all remember this data set. We have normalized it already. That is why all the ones here are 1, 1, 1, 1, 1. And then, of course, because we divided the values, it has changed the values here. But I'm still calling it X1 and X2. Okay. Now, remember that DMU4 is feasible within the above equations. It has to be feasible. It has to be identified within the parameters. It gives the optimum, reduction in the input level without, destroying the output. In other words, you can minimize the input given the output. And this can be solved using the linear programming problem that we are going to see. Now, we call this linear programming problem the envelopment problem. Now, if you have done linear programming, we always have something called a primal and the dual. Do you guys remember primal and dual?
Yes, Doc.
Good.
Yes, Doc.
Now, you would also remember that the objective function for the dual is usually going to use the constraint of the primal. Do you remember? The right-hand side of the constraint of the primal. Do you remember?
Yes.
So I'm just, recapitulating things you know already to help you. If you don't understand, guys, you say it. So that primal is what we call here in DEA envelopment model. Take note. And the dual is what we call here multiplier model. So take note of that. Keep that in mind, before we ever get there, because I'll be using those terminologies. So the envelopment DE model is the primal, which is what we are about to do now. And we are doing it for the DMU4. Now remember, we didn't say we are doing it for all the firms. We are only doing it for DMU4. But of course, with the advancement in technology, we are able to do it for all of them. So I want to assess the efficiency of DMU4 here mathematically Graphically, we've seen it. It would have been the distance to the frontier divided by the distance to the firm. Very easy. But life is not all about graphing. So how do you do it? The first thing you have to do is to form a constraint for each of the inputs. Watch it. And also form a constraint for each of the outputs. The input constraint, all of the inputs, and the output constraint, all of the outputs, that will be the same for every DMU because they make up the technology set. So this input and output make up the technology set. But I'm going to do it for DMU4. So after I've created the technology set, then I identify the coordinates of DMU4, its input and output, which is 3 and 2. It is that coordinate of DMU4, its resources, that is what I am trying to minimize. I'm trying to minimize this 3 and minimize this 2 to the best possible part of the frontier. I'm minimizing it till I hit the frontier. But I need something that will help me to minimize it. I need something. That is a decision variable again. I need something. Let me just take you back here. So you have the z equals to 40x1 plus 50x2. You remember for the Farmel Ghana Limited, this refers to what?
The profit maximization function.
Yeah. So what is this one here? What is it?
So the profit you get for selling Fan Yogo, I think at 40 and Fan Choco at 50.
Okay. Now, why didn't I add the 40 to the 50, but I have X? In other words, before I can get that profit, I must have identified the decision variable, isn't it?
Yes, Doctor.
I must have identified this decision variable. And I didn't identify that decision variable. Then I identified this decision variable, more or less. Because technically, a decision variable is more or less something that you don't know. And you got to now find, And in this case, once I find the X1 and the X2, I will find my Z. So I can choose to call Z the decision variable, but technically it is objective. At the end of the day, it's objective. It's the one we are looking for, the ultimate. Now, the same principle is going to come here. I need to find my decision variables. What are they? I need to find my lambdas. And then after finding my lambdas, I can use those lambdas to find my theta, which is my efficiency score. So I want you to see the efficiency score here as equivalent to the Z. Write it down somewhere. The efficiency score is equivalent to the Z. In my mind right now that I'm talking to you, I am seeing the entire picture of how I pull it out and reference each one of them. This is Z. But you see, I just told you that Z is objective function, but it's also the decision variable. It's also a decision variable. So this theta is also a decision variable, even though it's objective. Keep that in mind. So we are now going to form a constraint for the input, a constraint for the output. Now, how do you form a constraint? You just take this one, 2, and then weight it. So you do 2 lambda 1. The 1 here is simply, I would have just said 2 lambda. But I'm doing lambda 1 because that is for DME1. Then this one becomes 1 lambda 2. I'm just weighting each of the inputs. Then this one becomes 2 lambda 3. And I'll do the same thing for the X2. So I'll call this one X1 constraint. Do the same thing for the X2. Call it X2 constraint. Okay. And then do the same thing for the output and call it output constraint. They make up the PPS. They make up the technology. Okay. Now, what I'm saying is that all of this, the input one, all these inputs should be less than or equal to the input of this guy that I'm trying to assess. So if I have this guy here, okay, this guy, this number 3, this input 3, it can be greater than or equal to this whole thing put together. Or better still, this whole thing put together. Remember, this is an input orientation. That's why the inputs are 2. Or better still, this whole thing here put together with their weight must be less than that of 3 or equal to that of 3. I don't know now. But if it happens to be less than that of 3, then it means that 3 is too much. That's what it means. But if it is equal to that of 3, then it means that 3 is the lowest possible. It means it's on the frontier. And so 3 is the lowest possible information that 3 will actually have. So that is how you execute this thing very well. Do you understand?
Yes, Doc.
Okay. So I'm going to now use this mathematics now. We're going to do that now too, right? Okay. So this is how you formulate the efficiency of DMU4. Now, so you're saying that theta 4, I could have just written something like EFF4. I could have written that this is EFF subscript 4, EFF star, for you to see clearly that it is efficiency score of 4 that we are doing. But we are using theta to represent efficiency score for input-oriented measure. So the star here means what? Who can tell me? What does the star mean? Godwell.
I think the star that will represent the DMU after consideration when it is a model, the results we get.
You've made it complex. Make it simple.
And so the efficiency score for DMU4.
That is it. That is a simple one. So it is an efficiency score. It's a numerical score for DMU4 after the modeling has been done. So that equation, that first bullet, what is it saying? What is that first bullet basically saying? Jerry, are you here?
Doc, please, I am. I'm here.
Okay, go ahead. What is that equation saying?
Okay, so we are minimizing the efficiency of DMU4 subject to the
No, forget about the subject to. I want to understand. I want you to tell me in simple terms what that first one, bullet, what is it actually saying?
the minimum efficiency score of the weighted.
Did you just say the minimum efficiency score?
We are minimizing the efficiency score of DMU4 with the weighted averages.
What is he saying? Emily.
Okay, so I think we are finding the efficiencies of all the weighted DMU, as in no, Doc, please, it's not that clear.
What is not that clear?
How to explain that one? So we are saying the efficiency of DMU4 is being based on finding the I can't say minimize efficiency because efficiency, we want it to be 1. So that's why I'm having difficulty explaining that.
Why will you have difficulty explaining that?
Doc, can I come again?
Yes, come again.
So we are looking for the objective function of DMU4.
And that objective function of DMU4 is what?
That's the optimal technical efficiency score for DMU4.
Good. Yeah, we are looking for.
Yes.
And so you mean you've ended, you finished.
So what I'm saying that we are looking for the optimal technical efficiency score for DMU4.
Okay. You finished, right?
Yes, please, Doc.
That's what I wanted to share. You are looking for the efficiency score of DMU4. The star means we are looking for the numerical efficiency score of DMU4. But to get that, we need to minimize a contraction factor, or we need a contraction factor that would help minimize the input. We need a contraction factor. We need a contraction factor. We need a factor, an improvement factor. Okay, so this one here is not the efficiency score, but it's an improvement factor. A factor that is going to help us minimize the input of that DMU4 in order to get the actual efficiency score of DMU4. We need an improvement factor that can be used to minimize the inputs. I'm still here. I'm not gone down here. I'm still at the top. We need an improvement factor. And in this very example, the improvement here is contraction. So I can say the contractional factor because this is an input orientation. We need an improvement factor that can help us minimize the input, the too much input. Let's put it that way. We don't know it yet. The too much or too many inputs of DMU4 in order for DMU4 to be efficient with an efficiency score of theta 4 score. We need that improvement factor. But that improvement factor, to be able to get that improvement factor, you also need a certain weight. So we need an improvement factor and two decision variables. One of the decision variable is the weight. The other decision variable is the improvement factor itself. We need to minimize the input of DMU4 using this improvement factor. We don't know the improvement factor, but we know the DMU4, the inputs. So we're going to look for that improvement factor that can help us to minimize those inputs of DMU4 in order to calculate the efficiency score of DMU4. But to do that, now you bring your second part. To do that, you need to subject them. Now, I want you to see something here, that this DMU4 is objective function. This here is objective function. Okay, and the ones down here are the decision variables. Now, the decision variables are every single letter, okay, every single beta value or letter, like we had in the Famagana Limited. You have the X1 and X2. Every single letter or known variable, that is a decision variable. And when you come here, even if you don't see it here, when you come to the constraint, you will see that there are both theta as well as lambdas. So they make up the decision variables. So we need to make a decision. We need to find the variables, the decision. And the decisions are finding the values of the lambdas. Once I get the values of the lambdas, I can get the theta. How do you know that? Well, if I get the value of this to be 0, the value of this to be 0, the value of this to be 0, if I get the value of this, okay, so let's say that the value of this is 0.5 and the value of this is 0.5. Then what it means is I can now find my theta, can't I? Oh, sorry. So this is 0, this is 0. Let me just undo this. Okay. So all of the first three are 0. But then this last one is 0.5. Okay, if I find that value. And this one too is 0.5. I had to make this 1.5 because they will add up to 1. Then it means that I can know these two values, can't I? And if I know these two values, I can now find my theta value. Are you guys with me?
Yes, Doc.
Yes, Doc.
So this is an optimization problem. The optimization problem is to find these decision variables. And also, once you found this decision variable, it will help you to find this very decision variable. And when you find this very decision variable, that will be able to be used to be able to calculate this one. Now, how do you do that? How can you use it? Because remember, theta is here and theta is there. Well, if I'm able to get the value here to be, say, 1.5 here and then 1.5 there, I add the 1.5, 1.5 together, what do I get? I get 3 for the left-hand side. Now, I have this 3 less than or equal to 3 theta. Okay, which means that theta is going to be what? Approximately 1. But then it can also be less than what? 1, isn't it?
Yeah.
Because the symbol here means that it can also be less than 1. So there are multiple possibilities of theta. Okay, so you've gotten theta value, but the values are different. It can be 1 or it can be less than 1. But we know that the highest value theta can now take here is 1. Okay, but what the same thing will be here. You have gotten this value. But the fact that you would have gotten this value does not mean that you've now been able to calculate the efficiency. Because we still need to find this. But you just told me that it can be any of this. So once you get those values, this efficiency term is, this efficiency of star what 4 is going to be the target value over the actual value. So now I knew the actual value of this guy. Okay. For example, the actual value of DME4 is the weighted output, is a target, and the target is this. Okay. So the target will be 3 theta. Okay. I need to find it for one of them. Okay. The target is 3 theta by the actual, which is 3. And then I need to do the same thing for the other one. Okay, the target by the actual. So I can do the target but by then I have to get multiple values. If I even do here, the target by the actual, okay, it tells you that the value of this is going to be 1. If I know the target, because the target is this one. Okay, but then if I have been able to find the maximum value this can take, which is 1, right? If I get a maximum value this can take, then it means that I'm going to have 3 divided by 3, making the efficiency score 1. So your ability to be able to find the efficiency score requires that improvement factor capable of minimizing the input and the output. Of course, everything that you see here is a convexity constraint, which is designed for the variable retention scale assumption. If you drop that, then you have a constant retention scale assumption. Now, I have a question for you. You see that you have this final bit here to be theta free. What does that theta free imply? What does a theta free imply? I'm going to let you formulate your own very soon. So it's very important you understand. What does a theta free imply? Emily.
No, please, I'm not sure.
Hey, Wampa. So like today you are blocked, right? It's like you've never studied this thing before. Should I? Yes, go ahead.
Can we say that it indicates that it is not restricted?
What is restricted?
It means that the theta is not restricted. It can take any form of a variable, be negative, 0, or
It's true, it can. It's true that it can take any form of variable, but based on what? Why? Why will it take any form of variable? Based on what assumption will it take any form of variable?
based on the assumption that input can be efficiency can be either negative positive or zero?
Oh, negative? Did you use the word negative? I'm sure you want to include that one.
Those assumptions that efficiency can be positive, zero, or uniform.
Sorry, I didn't hear the last one. Positive
I
zero
said,
what?
based on the assumption that efficiency can be either positive or zero.
It can be positive or zero. You see, that free implies that that particular DMU that you are looking for can be operating under the constant because you've already allowed for VRS. So it means that it can be operating under DRS, decreasing returns, constant returns, or increasing returns. That's what it means. It can be operating there. And because it's got a capacity or the ability to be operating there, that is why. That is the essence of that very assumption. Does that make sense?
Yes, look.
You are allowing it to have those values. In other words, you are allowing it because you say the return to scale is variable. So you are allowing it to have the value is free. It's free. So you are allowing theta is free means that it forces the returns to scale to be constant, variable, to be constant or decreasing or increasing. And those are possibilities. And that is why he said that it has to be free. Okay. So let's move on if there is no question on this. So this is how you do a formulation for DMU4. Now, if you were to do a formulation for DMU1, what will change? And what will not change? Guado, what will change and what will not change?
Okay, so for DMU1, what would likely change is the very first objective function, theta star 1, and also the constraints. The left-hand side would be the same primarily, but the right-hand side will have the values for the inputs and output for 1.
And what is that?
So if I go to the data,
You don't need the data.
DMU1,
You have everything
okay,
here.
okay, good. So we shall have in the input x1, we shall have 2, the input x2, we shall have 5 there. The output is already 1.
Good. Excellent. So that's it. Any question on this? So you should be able to learn how to formulate. Now, why would you say that you wouldn't touch the left-hand side?
Because in the text set, the whole input should be less than that of the...
No, I didn't ask of the technology. I'm saying,
Okay.
why would you say, why did you say you will not touch the left-hand side of the equations?
Okay. Because of the formulation, all inputs should be less or equal to the right-hand side of the DML consideration.
Okay. What else did you say? Albert, why would you not touch the left-hand side?
Look, because essentially the constraints, the weighted constraint factors are the same across the DMUs.
The weighted constraint factors, I like that. But practically, why would you not touch the left-hand side? Emily.
But because the weights are the same for each DMU.
You are repeating what she just said. Why would you not touch? Jerry, you have been thinking outside the box. Let me see whether you get this.
Good.
Why would you not touch it? Because that is a technology. I said it some minutes back. That is a technology, and the technology is for all of them. The technology is what all of them are facing. So you don't have to change the technology. That is why the left-hand side is untouched. Okay. So Normally in class when I'm teaching this physically, what I do is I go around. Then I tell you, formulate this one, you two formulate that one, you two formulate for DME1, you two formulate for DME5, but you should formulate for DME2. Then I check whether everybody will be able to do the formulation. But I think you can, can't you? Now, Godwell, what you
Yes.
got to do is to formulate a simple hypothetical example like this for
Okay.
a DEA before
Okay.
you do the same for the SBM.
Okay.
It's very important too. And in your case, you are also using VRS, isn't it?
Yes, please.
So you have to do that for both DEA and SBM. Okay.
Okay.
So what is the whole linear programming doing? We've said it millions of times. The LP seeks the efficiency score for DMU4, which is called theta star, 4 star, by reducing the input, using a factor. That is what I call the improvement factor. Using the improvement factor. The improvement factor happens to be the decision variable. Okay, but it's not the only decision variable. There is another decision variable, which is the weight. The improvement factor is also the objective function of the linear programming. Of course, this is a linear programming problem. And he's doing that minimization subject to the constraint that the weighted sum of the inputs, both input X1 and X2, okay, of all the DMUs is less than or equal to the input and the input of that particular DMU whose efficiency you are trying to assess, as well as the weighted sum of the output of all, the word all is very important, of all the DMUs, that should be greater than the output of the DMU that you are assessing. You got to understand the mathematics and the interpretation of this formulation. Any question? All right. There are a few things you need to note about the theta. Okay. The theta, the efficiency score, is added to the current input of the DMU. And you saw it on the right-hand side. We added it. Okay. We added it here. Why did we add it? Why did we add it? Why are we multiplying it? Because that is improvement factor. Okay, that is improvement. So it's like he's doing a dual role. You is the one that you're trying to minimize. It's an unknown variable you're trying to minimize, but it becomes efficiency score or the objective after you've gotten it. But you only get it provided you've been able to weight the input and the output. Okay. And because this is an input orientation, the output are kept constant. And that's what I have here. Can you formulate similar ones for the other DMUs? The left-hand side is not changed. Okay. And the right-hand side is all of that. Okay. Let's go to the lambdas, the weights. The weights, the lambdas, they're also called the multipliers. Now remember here, the multipliers here are the multipliers for the DMUs, not the multipliers for the inputs. Take note of that. We are talking about the weighted sum of input. You see, the weights are assigned to the DMUs. They are not assigned to, so when you come here, you see, if you check weight, I'm not assigning the weight to the input X1 because the input and the output are just X1 and X2. But we have lambdas are up to what? 5. So it means that the weights are not in the variable section. So suppose you have a whole data frame, okay, a data frame of variables here, and then the rows are DMUs, okay. The weights, the envelopment formulated weights are not for the columns, they are for the rows, the DMUs. Take note of that. Because when it comes to the multiplier one, they are for the columns. That's how I mentioned it. When it comes to the multiplier formulation, the weights are going to be for the variables. But then for the envelopment formulation, the weights are for the DMUs. Take note of that. Okay. First, you have to identify the weight. Now, you also notice that the weight is the lambda is the weight of the PS. Now, I say the weight of the PS, but what if there are no PS? Well, then the DMUs also have weight. So it's not just the PS, just that The lambdas for those that are not peers are 0. Okay. So technically, it's not necessarily the weights of the peers, but they are the ones that will have a non-zero weight. The peers will have a non-zero weight. Who are the peers? Well, the peers are identified. We'll talk about the peers very soon. So those DMUs with non-zero lambdas, they are the ones, that serve as the peers. Another word for them is efficient reference. Another word for them is role models. Another word for them is peers. They serve as peers for the DMU that you are trying to assess. Now, the DMU that you are trying to assess, we always use DMU not. Okay. I think the word target DMU is not nice. The word is DMU under evaluation. Okay. Because other than that, it makes it look like that's the one we are looking for. The target, that's what we are looking for, but it's not. The entire left-hand side for each equation is a PPS. We've said that. And the right-hand side is something that belongs to the PPS. So what does the theta do? Let me ask one of you, because you should be able to explain this. Because these are the questions when you're presenting, somebody asks you, what does the theta do? Jerry?
Well,
Albert? Mm-hmm.
no,
Yeah, go ahead. I'm listening.
the theta.
Yeah, what does it do?
It is looking at, it measures.
You sound far away.
Doc, can I come in?
Yeah.
Okay, I think you mentioned that the theta was the improvement factor.
Yeah.
And
So what does
so,
it do? That's what I mean.
okay.
Okay,
Doc,
Doc. So,
it's helping the DMU to. Okay, Albert, you can come in.
okay, Doc. So, yes, theta is the efficiency score for a DMU. In the inputs and the output formulation, the constraints, we saw that we multiply the right-hand side by the input of the DMU under consideration. So if perhaps the right-hand side was a value of, say, 10, and we got theta for that DMU to be, say, 0.9, it means 10 times 0.9 will give us 9. It means that the DMU should go to reduce its input instead of from 10 to 9. So it's telling by how much you can improve your inputs for that particular DMU.
Okay. What does the theta do? I've said this thing before, so I'm expecting it to be just repeated. What does the theta do? Yes, Albert Ben Susan.
Look, I think it's the contraction or expansion factor that helps like the right-hand side match up with the left-hand side.
Yeah, that's mathematical. What is it doing, really? Practically, what is it doing? You see, I didn't say what does theta star do. That's why Goddo, when you said that is efficiency, it becomes efficiency score later. But this one is not the theta star. This is theta. What is theta doing? I hope you guys are taking notes. What theta is doing is that theta is being used to reduce, in this case, the input. Theta, what it is doing is to help us. Albert, you said it, that is a contraction factor, but you brought the mathematical side of it. That is on the right-hand side. But what is it doing? It is helping us to reduce the input of that particular DMU and evaluation, we are reducing those inputs from inside the frontier or the technology to the boundary of the production possibility set. It is helping in that reduction process. You see, anytime you are doing this input and orientation, have this graph in mind. The whole thing is like this. And this DMU4 is somewhere here. And theta is trying to bring it down to the frontier using the radial fashion. And theta is improvement factor, but it is, how is it improving? It's reducing the input of the DMU under evaluation to the frontier. Take note of that. So if you have a particular theta value of 71% or 71.4%, I was going to ask that, but you see it here already. What does that mean? What does that mean? If you have a theta value, you see now I said theta value, that is theta star, not just theta, a theta value. And the value now is 71%. That means that 71% of the current input, watch it, 71% of the current inputs of the DMU4 is feasible in the PPS. Now, this is not interpretation. This is a meaning. In other words, when you take DMU4, if 71% times, that is multiplying, the current input of the DMU, make that input feasible within the PPS. Now, as to whether it makes it efficient is a different thing. We'll look at that together. But it makes it feasible within the frontier. All right. If you understand it, let me know. So the optimal value, which now is theta star, of the objective function, which is theta, okay, is the input efficiency score for the DMU. Now the whole thing is clear. The optimal value is the theta value. That is a theta star. That becomes the efficiency score of the DMU. But it is the objective function. Okay. The objective function is this one. But the objective function is a function. It's a function. It's not a value. There's a difference between objective function and objective value. The objective value is theta star. The objective function is theta. I think you guys get it, don't you? So, using this graph, let's go back to the graph here. Okay, using this graph, we should be able to now identify all the elements that are necessary. Okay, so Emily, walk us through everyone that is efficient and everyone that is inefficient and why.
Okay, so from that graph, we can see that DMU2 and then DMU5 are efficient because they are on the frontier. And then on the other side, we have DMU1, DMU3, and DMU4 being inefficient because they are inside the frontier. Now, we have also the DMU3 star, which in this case will be the target efficiency for the DMU3, because in the if they are able to move from where they are to the 3 star, that will make them efficient. And the way to get that 3 star, we did one last week, and then we've also looked at one now where we are saying that if we find the theta and we multiply it by the current value of the DMU3, we'll be able to get the 3 star where the 3 star is.
Very
So
good.
it will show us, okay.
Continue.
Doc, I've received my very good already. Okay, so that will show us the reduction needed in order to reduce the input to get to where the 3 star is.
Is that all? Are you done?
Yes, Doc, I'm done.
All right, okay. So you have this. So now we are going to write the technical efficiency general formula. And by the way, this general formula we're going to put down, that is the one you will submit to your work. That is what you will now show. This is what you also see, what you're about to see. That's what you also see in journal articles. That is the proper technical efficiency measure Everything we've done, we've used a hypothetical data, but now we are going to look at the actual input. This is input efficiency of a DMU, a particular DMU. We need the DMUs, the input-output combination for that DMU. It has to be feasible within the production possibility there. It has to give the optimum contraction to the input level, given the output level. So what you're about to see is the envelopment formulation. Okay. When you now learn the multiplier formulation, and by the way, this is input. So I'm going to ask you to do the output. What will change in the output? 6 things will change. So you got to be able to follow what we're about to do. Okay. So this is an input oriented. I want you to look at it well and identify what would change in the output looking at this. But first, look at this input. Just a second. All right. So everybody's going to tell me one of the things that would change in the output since you all understand the input. Unless you have a question here, let me know. If you have a question before we ask, let me know because I'm going to be asking you things. This is what you normally put down by in a presentation or in a journal, and you got to understand it fully. Okay. If there's no question, let me first ask you a question here before we go to how to change it to the output. Starting with Godwell. What does the lambda J mean? What does the J in the lambda mean?
Okay, so the J are the weights for all the DMUs.
The what?
The weights for the DMUs.
What is the weight?
So the weights are
No, you said the what is the weight?
the lambda is the weight.
You said the J are the weight.
No, for the DMUs, the DMUs.
Okay. So what is the J?
So the J's are the
What is the J?
DMUs. So a particular DMU 1 to N.
Sorry?
So the J is for one particular DMU.
The J is one particular DMU, and the J are how many?
From 1 to N, so here 5.
Okay, all right. So that is the first part I'm asking. Second, what is the 0 here? The 0. Albert Bensusan, the 0 here, what does it mean?
Doc, the final 0 is the non-negativity. So the lambda should be greater than or equal to 0. So you can't have a 0. Yeah.
You said the 0 is what?
So we are saying that the lambda should be greater than or equal
No,
to.
no. I just pointed here. I said this 0. What does it mean? That's all I'm asking.
Oh, sorry. X from I to A.
So if you're writing a model, you got to understand what the model stands for. Because anytime you don't understand what you've written, that's what people do. You come and put a model down, they don't understand the elements of the model. Then they say that, oh, this is it. You can act like you know,
No,
but
I don't know that
if you
one.
don't know, you got to know.
I don't know that one.
Okay, so let's go to Jerry. What does what does the not mean?
It means it's considering it's talking about the particular DMU you are evaluating.
Okay, such as what?
such as maybe DM. So up there we have DM1, DM2, DM3.
Very good. So if we were evaluating DMU4, what would change here? What would be the value of the knot?
4.
Sorry?
4.
Yeah, it would have been 4. That would be great. But then when you write 4, it will not make sense. It would be rather better to write DMU4
Yeah, okay.
instead of 4, because the I2, there's 4 there. You see the R and the I, that one too, there's 4 in them, right?
Yes, please.
So you have to be specific what it is, because this one is not a number, it's a DMU name. So if the DMU was a bank and it's GCB, that is what you would have written the GCB. So if you are formulating and you are using a hypothetical data and your hypothetical data are banks, that is what you got to do. And it makes practical sense when you're writing your thesis and you are demonstrating. It's nicer when you are using names of practical companies and you are formulating them from that perspective than just using A, B, 1, 2. Do you guys get what I mean? You get what I mean?
Yes, Doc.
Emily, what do
Yes,
you get?
Doc.
What do you get?
Okay, so if you are having the actual DMU name there, or like you make it specific, like this is the DMU you are referring to, it makes it nicer.
That means that in your data set, it must already have what?
The data set should already have the DMU names.
Such as. Don't use the bank.
Okay, so if you are doing universities in Ghana, the DMU name should be there as in KUST, Legon, like all the investing actual names should be there.
Good. Okay, it's very important. It makes things very practical. All right. So now, what is going to change in this if we were doing an output orientation instead of an input orientation? What is going to change? Everybody is going to tell me. So just tell me yours first before somebody goes to say, before you come and say that, hey, sorry, I was going to say that.
So I'll start.
Okay, go ahead.
Okay, so with the objective function, it's going to change from theta to phi.
Okay. So you mean everywhere we see theta, we put in phi.
Yes. And then the minimum will be changed to maximum.
Okay, fine. What else?
Next person
Hey,
after me.
no, next person.
So if we're doing the output, it will be subject
Sorry, you
to
sound very far away.
it will be subject to output constraints.
What is that?
So would have had
Do you see anything subject to input constraint here? Is the word input constraint written?
we have so if it were output, the x would have been y.
What would have been y?
The x.
The x.
Yes.
You mean this x here?
Yes, please.
This x here will change to y?
Yes, no.
No, it will not. It will not at all. You remember we said that the left-hand side of the equation never changes. Do you remember?
Okay.
Next.
But the sign,
What sign?
the first sign would have been greater than or equals to theta x.
No. The sign wouldn't have changed.
Hey.
The sign would have remained exactly as it is. What else would have changed? Emily, help them.
Okay, so Doc, when we come to the next,
And
the
please
first
write it down. Write it down because here is the problem. The problem is that sometimes you think you know, and so you don't write it. Okay. And even when you are taught, you don't write it. Because the question I'm asking here, the answer is not in the slide. So not writing things. In fact, one professor said that the worst form of learning is not writing and trusting that you remember it. 90% of everything we are talking about here, you will forget it. If I were to even ask you some of the ones we've just done, you forget. So writing keeps memories. All right, Emily, continue.
Okay, so for the first constraint, the only thing that will change is that the theta will be removed since we are no longer using the input. So it will just be less than or equal to xi0.
Continue.
Okay, so that's what will change there. And then when we come to the second constraint, here, because we are now doing output, the phi will be attached to the right-hand side. So it will be phi yr naught.
By the way, when she talks about phi, she's talking about this symbol. Okay, good. What else?
Yes. The convexity constraint will remain the same, and then non-negativity constraint will also remain the same.
Very good. So two things are the main things that will change here. Take note of that. So that is how you do the formulation, okay, and how you distinguish the input orientation from the output orientation. It's very important that you know these things and you master it, because once you don't get, you see, you are at a level you got to teach yourself. That if you don't get these basics, you can't teach yourself well. All right. So efficiency score eventually is going to be between 0 and 1 because we are dealing with input orientation here. The xi naught and the yr naught are the ith and the rth output of the DMU under consideration. The one you get a value is the input oriented efficiency score. If it is equal to 1, it simply means that there is no way that particular DMU can anymore cut down resources. There's no way, again, radially speaking or proportionally speaking, they cannot, which means that the firm is a frontier DMU or is efficient. If it is less than 1, the firm is dominated by the frontier, and hence that firm is a non-frontier DMU and hence inefficient. So what the linear programming is doing is that is looking to find an efficiency rating of the target DMU. Now, what is a target DMU? Godwell. What is a target DMU, Godwell?
Look, I think the target DMU here is a DMU under consideration, or the DMU that is benchmarking, the DMU which is being benchmarked.
Okay. The target DMU, you said, is the DMU benchmark. But I said earlier that that word shouldn't have been targeted. What should have been?
Yes, so it's under consideration.
Okay, good. So what it's doing here is that you are minimizing the data subject to the constraint that the weighted sum of the inputs of all DMUs is less than the input of the DMU being evaluated. And the same thing with the output. So this is the data set we have been dealing with. We've gone through deeply the mathematical ambience of how to formulate this thing. We also remember the way we did the graphing of this data set. Now, we know that DMU3 is inefficient because it's inside the frontier and that. But its input efficiency is measured relative to the theta prime. Okay. Now, what is 3 prime? What is 3 prime here? What is a 3 prime? What is a 3 prime here? Jerry, what is 3 prime?
Well, it's talking about the score that DMU3 has to reduce to be able to, the input that it has to reduce to be able to be on the frontier.
No. What is 3 prime? Emily?
Doc, is it the distance from the origin to the frontier of DM3?
That is the target efficiency score for DME3.
That is it. It's a target efficiency score for DME3. But what is 3 prime? The 3 prime here represents what? What do you mean by the target efficiency score? What is that? What is that?
Look, I think it's the potential for DMU3, assuming they became efficient.
Potential what? Potential what?
Efficiency. Optimal efficiency.
Optimal. Yeah, but what created that optimal efficiency? That's what I want. That optimal efficiency, that 3 prime as it stands, what is creating it? How do you get that 3 prime? You see, if you talk about this for the management, the manager will not understand. Okay. Yeah, Emily, go ahead.
Doc, is the reduced input.
Good.
So
you are connecting it to the input. You see, when you speak in terms of efficiency, you confuse managerial insight. Continue.
Okay, so at 3 prime, that means the current inputs have been reduced to meet the frontier.
Good. So
at that point,
when you said is a target efficiency, you could have rather said is a target what?
is the target input
Exactly.
that the firm can use.
So is a targeted input that a firm needs to use, not what DME3 is currently using. It's currently using this input, which is 2, but then the actual input or the targeted input is supposed to use is this very one, which is 1.7 something. So understand the thing from that. Okay. Now, where does 3 come from? Is it a real DMU? Where does 3 come from? Is it a real DMU? Godo.
Yeah, 3 is a real DMU, but 3 prime is not. It's imaginary.
Okay, sorry, I mean 3 prime. 3 prime. Where
Yeah,
does
3 prime is not a real DMU. It's imaginary.
What is it?
So that is what we want DMU to 3 to get to.
Is it a DMU?
It is not imaginary DMU.
No. Is it a DMU? 3 prime. Is it a DMU?
No, it is not.
It's not a visual DMU.
I don't ask me a question with a question. I said, is it a DMU?
It's not.
That's a visual. Please, it's a visual DMU.
It is a DMU, Godo. It is a DMU. It's just that it is a virtual DMU.
Okay.
It is a hypothetical DMU. 3 is a real DMU, but 3 prime is a virtual DMU. It's a linear combination of DMU2 and DMU5. Therefore, it's a virtual DMU. Okay. And 3 prime is the efficient input reduction, efficient proportional reduction of all the inputs at the same time. Of course, you see, when you look at it, that it will be the best virtual guy for DME3 because it's on the same pathway. But DME2 and 5, which one of them dominates DME3 the most? DME2 and DME5, which one dominates the most? Or which one will DME3 learn from the most? Because they are real. They are not virtual. So they are more or less the peers of DME3. 3 prime is not real. But 3 prime itself was created by the converse combination of DME2 and 5. So DME3 need to get somebody to learn from in real life. You have to go to real DMUs, which is 2 and 5. Which one is it going to learn the most from and why? Albert Bensison.
Doc, please, DMU2.
Why?
Primarily because it's closer to DMU2. The reduction in the use of X1 over Y will be like the only factor that you need to consider because they're essentially on the same for the x2 over y.
Okay. All right, very good. There's something technical there, but we'll talk about that, at a later time. All right. So even though DMU 3 prime is a converse combination of, we said DMU 2 and 5, but technically it's not DMU 2 and 5. It's DMU 1 all the way to 5. It's everybody. Remember, it's a relative measure. But the only reason why we are saying it's DMU 2 and 5 is because the weight attached to the other DMUs was 0. At the time, it was DMU 3 was doing the linear combination. It placed a 0 weight on the others and put all the weight on DMU 2 and 5. That is why it looks like it's only a linear combination of DMU 2 and 5, but it is for all of them. All right. This measure is also radial measure. It's not non-radial. It's radial, which means that it is a proportional input and output reduction. Okay. And in this very example, you are decreasing the input, holding the output constant. Or you can raise the output given the input levels. All right. Now, when you are measuring the input efficiency of a DME3, we have to preserve the input mix and reduce all the input proportionally. But the mix has to be reserved. The mix has to be reserved. So your understanding of mix efficiency is very important here. Mixing, preserving the ratio 2 to 2 between X. Now, why are we saying 2 to 2? Okay, because when you go to the graph here, when you are at DME3 here, the inputs that are being used on the X1 axis is 2. And the input being used on the Y-axis here is also 2. So this ratio of 2 to 2 has to be preserved each time you are moving along this curve. Each time you are moving, you got to preserve the input. And that preservation of the input mix is the reason why we are on the radial path. Because the only way you can preserve the input is moving on the radial path. Okay. Now, so we call it proportional reduction of inputs or the direction towards the origin. We know that graphically. Okay, so DME3 is also called the benchmark or the efficient target for DME. D3 prime is a benchmark. Technically speaking, that word benchmark, sometimes it is used for the target. Okay, but it's also sometimes used for the virtual, but it's also sometimes used for the real DMU. So take note. The benchmark is actually the target, the efficient target. But you can also have a target that is not an efficient target. Do you know that? Do you know that you can have a target that is not an efficient target? I mean, it's a weakly efficient, so it's not a strongly efficient target. Okay. DME3 is not real. Rather, DME2 and 5 are real. Those are the role model. But then DME3 has got 3 characteristics. DME3 prime has got 3 characteristics that is very important. The first one is that it's feasible. The second is that it dominates the 3. So nobody is as perfect comparison than, DME3. And then it also produces the same outputs that 3 is producing. So it's an excellent benchmark for 3. This is the formulation that we did. Never forget how to do the formulation for the other. Okay. All of these are examinable questions. So when you solve for the linear programming for DME2, what do you get? Well, if you go and solve it, because we can't solve it here because we have to use a linear programming, and we'll do a linear programming. Okay. But when you solve it using Excel, using R, using Python, or any linear programming, Lindo, any of the softwares, MATLAB, you are going to realize that, and listen here, this is important. You are going to realize that the DMU4 has got an efficiency score of 71%. That is efficiency score that it has. That's what you're going to realize. Oh. Okay. You're going to realize that it has that efficiency score. And that will mean that it's inefficient. It will have a lambda score. I say it will have because you have not calculated it yet. It will have a lambda score for DME2 to be 43% approximately. As you can see, 43% for DME2. So that's why this is a lambda 2. And then it will have a lambda score for DME5 to be 57%. Okay, 57%. You know, the beauty of this is that it's using 2 and 5 as the role models. Remember that DME3 also used 2 and 5. But DME3, if you can remember, would have put more weight on DME2 as a role model than it would have for DME5. But for DME4, it rather put more weight on DME5 than it is. All the others that are not 2 and 4, their weight on them was 0 in this case. Now, these weights, these lambdas, these multipliers, they are very important, and we'll talk about them because they are the ones you will need to use to get the target for DME4. Remember, we said that the DME4, when you check DME4, the inputs and outputs is using are 3 and 2. These are not good. We need to cut down the input 3 down and input 2 down. Okay, there we know that the efficiency score would have helped us to do that. So watch it, we are going to do that. Okay, there are 2 ways to cut the input 3 down and input 2 down. One is using the efficiency score, the other is using the lambdas. Guys, write that down. I always ask exam questions on this. And this is input orientation, and when it is output orientation, it's a little bit tricky. Godwin, what did I say?
Is that the output orientation a bit tricky?
Yeah, but I mean, what did I say before that?
To come in exams, but when it comes to the lambdas, the 4 is using the 2.
What are we using what for? For what? We are using the what to get what?
Okay, so when we solve the model, DME4 is inefficient, yes. The theta score was 0.71 for efficiency score. But the lambdas that were given, so lambda 2 and lambda 5, it suggests that those 2 are the benchmarks. But because lambda 5 has more value, I was putting more weight from lambda 5 than lambda 2.
Okay.
As the PS.
Okay. Yeah, but what are you calculating? What are we looking for? We are calculating the target. This is what I said that I wanted you to repeat.
Okay.
We are calculating the target. And I said there are 2 ways of calculating the target. What are they?
Okay, so the first one will be the lambdas multiplying the scores, the PS, the values of the PS.
What values of the PS?
So the input values of the PS.
You mean the actual values of the PS?
Yes.
Good.
And then the second way is to multiply the efficiency score with the input value of the firm's own score.
This is very important, guys. What she said is very important. If you didn't hear it, let her repeat it so that you document that. Did you hear it?
This is the second one.
Okay, the second one is the theta, that's the efficiency score, multiplying the input of the firm's own input.
Thank you.
Okay. All right, any question? So, as an example, this particular DMU4 had an input X1 of 3. In order to reduce it, we took the lambdas. This was the first lambda, 0.429. but it's a lambda from DMU2 because it's learning from DMU2. 4 is learning from DMU2. And this is a lambda for DMU5. So we take these lambdas, we multiply this lambda here for DMU2 by DMU2's input, not by the input of the DMU4 we are assessing. And then we take this 0.5171, we multiply this lambda of DMU5 by DMU5's input. And that is their input to X1. And that will give us the target for DMU3. It's X1 target. And so that is what you see here. We add them. This addition property is very important to understand. The same thing, this guy here, the same DMU4 had an input of 2. Is inefficient. We know that from the efficiency score of 0.71. And then we took that and we took the same lambdas. Remember, we've done it for the input X1. We got to do the same thing for input X2. And that's what we did for the input X2. Input X2 of the peers actuals. The actuals of the peers. So please take note. Now, can you confirm that using the theta approach would also lead to the same thing? Can any of you confirm? How would you have calculated that? The theta approach. If you were to do the theta approach, how would you go about it? Jerry? Jerry?
Oh,
If you were to use what we just used was the target, the lambda approach. But if you were to use the theta, the efficiency score approach, how would you go about it? If you don't know, say that you want help.
okay, I want help.
Pick anybody.
Okay, so
yeah, Emily, go ahead.
okay, so the theta for DMU4 was 0.714. So you can take that one, 0.714, multiplying the actual score for DMU4, which was 3. And that will give you the first one, which is the 2.142. And then if you use it to multiply the other one, which is 2, you're going to get the 1.43.
Okay, so Jerry, thank you. What are you multiplying? What are you multiplying what by to get what?
We are multiplying the efficiency.
No. Tell me the numbers you are using to multiply what? We are dealing with DMU4 here.
DMU4. Let me check on that. So we multiply the score of DMU4, which is I'm coming with the phone. So the DMU4 is 0.714. So we multiply it by
You see, she just said it. But I knew that you didn't understand. And normally when you don't understand, you're supposed to ask. But because you didn't ask, that's why I'm asking you. And now you're stuck. Because there's a distraction in where you are. Normally, online work, that's what happens. Distractions upon distraction. You feel so free that you don't even pay attention. So free, you're doing your own thing. You just connect and then you make it look like you are here. But you are hurting your own self.
pressure. Some pressure.
Pressure from who? You have dedicated this time to learn. What is the pressure from?
No, Prof. Martin has just sent us a message that we should submit some work right now.
Look at him. Okay, so you do the multiplication, you get 2. Emily, was there an when you do that multiplication, is there any decimal differences from the 2.142?
No.
No.
All right. So that's it. That's how you execute this. Very, very important. This is very important. Okay. Going forward, you can do the same thing. This becomes the virtual for DMU4, and they are also the benchmark or the target for DMU4. We can modify the full model to assess the technical efficiency of any other DMU that we have done. So we can assess the DMU1, efficiency like this, okay? And we can see that the difference, we've spoken about this. You can see that the differences are different from this. Okay, now we are going to look at returns to scale. Okay, we are going to look at returns to scale here. We'll do that in the next few minutes before we wrap up. So we are going to give ourselves 10 minutes. Okay, 10 minutes relaxation, 10 minutes stretching, 10 minutes something, and then we'll come back. It's 9:55. We'll come back 10:05. Okay, and then we'll come and wrap up with scale efficiency. Is that fine by all of you?
Yes,
Fine,
Doc.
Doc.
Emily, you've been eating longer, so I'll give you extra
No,
5 minutes. We already know about scale efficiency, but I want to get it once and for all. Now, that Chance Cooper and Rose, that paper, it assumed that firms are operating at the same optimal scale size. That's like in the robotic industry. So if you double the inputs, the output will double. If you triple the inputs, the outputs will double. But in real life, because of government regulations like minimum capital requirement for banks, because of imperfect competition, so the law of one price doesn't stand, because of constraints on finance, okay, because a company is going bankrupt, because of innovation, it will not make all the firms operate at the same optimal scales. Some will be bigger, some will be smaller, some will be more innovative. Others, because of measures and acquisition and all of the consolidations, it can cause a particular DMU not to be operating at the same optimal scale size like another one. Hence, this principle of variable returns came into the picture. It came 6 years after the original one. And using that variable returns, you can now decompose the overall technical efficiency into the pure part and the scale part. Albert Bensis, are you with me?
Yes, Doc, I'm here.
Now, the pure part here and the scale part is very important for you to understand. At first, note that if you're a service company, mostly they are operating at variable returns. And manufacturing robotic-like company, where it is they follow the same trajectory, they operate using constant returns scale. But in reality, if you want to know whether the industry, not a firm, the industry is operating at a constant return of variable returns to scale technology, you got to test it statistically. We'll do that at a later time. Albert, sorry, not Albert, Godwin, I think you did that, right?
Yes, please, Doc.
Yes. So when we get there, you will speak to that a lot. So those codes that you just did that, if you don't understand, go get help from that chat guy to explain the codes for you, because I know you were just putting in the codes and getting answers, have you?
Yeah.
So returns to scale is used to feature different models, but it has to do with the shape of the frontier. There are two kinds of frontier. The best practice frontier, that is a VRS, and the benchmark frontier, that is a CRS. Now, under the VRS, because of the variability, the firm, you see, watch it, the firm, not the industry, the firm can be operating at constant increasing or decreasing returns to scale. But the industry itself, I just spoke about constant and variable, but there are aspect, there is a non-increasing and non-decreasing returns scale. So it's not just constant and variable returns, but also non-increasing and non-decreasing. This video here, when I click on it, is going to explain the nitty-gritties of all of them for you. So let's try to understand the local returns to scale. You see, everything we said before is what? The global returns to scale or the industry returns to scale. That's what we spoke about. And we've already concluded that the industry returns to scale has got 4 different types. Emily, mention all 4. The industry has got 4.
Okay, Doc, we have the I know of 3 others.
Mention them.
So we have
Mention the 3.
okay. So we have the increasing returns to scale, the constant returns to scale, and then the decreasing returns to scale.
Good. Now, returns to scale assesses the connection between inputs and output in the long run. Economies of scale measures the firm's long-run average cost as that responses to the changes in the input. So if you produce more because you are big, you spread the cost over the large production. That is economies of scale. But local returns to scale is achieved by estimating the the technical efficiency under VRS, under CRS, and under NIRS. Local. You have to estimate under all of them. And when you estimate under all of them, you can now use that to find the individual firm level returns to scale. If you want the VRS, you got to implant this convexity constraint here. If not, you see the convexity constraint shows equality. Once you show less than or equal to, you are introducing the non-increasing returns to scale. And that takes care. What is the difference between the 2 equations? What does that tell you? What is the difference? Okay. So it looks like you all got that. Suppose you calculate the technical efficiency under CRS and you calculate the technical efficiency under VRS, and they are the same. It means that that firm is scale efficient. So the scale efficiency score will be equal to 1. Scale efficiency is given by the technical efficiency under the CRS divided by the technical efficiency under the VRS. Take note. If it is not, then we have to now go ahead and compare the technical efficiency under VRS with that of the NIRS, the other technology one. If they are equal, if the NIRS and the VRS are the same, the firm is inefficient, scale inefficient. But if it is not the same, the firm is, so the firm is scale inefficient in the first place, but is experiencing increasing returns to scale. Okay, increasing returns. And if it's not equal, if the TE NIRS is not the same as TE VRS, then the firm is experiencing, it's also scale inefficient, but is under decreasing returns to scale. Now, the software called DEAR will do all of this easily for you. So in your research, one of you, in your research, like you, Emily, you are doing cost efficiency first time, you can dictate that the cost efficiency, under the cost efficiency, is there, what is the nature of the returns to scale there? At the firm level, what is the nature of returns to scale? You can incorporate that hypothesis. Are you with me?
Yes, Doc.
All right. Now, scale efficiency can be obtained from the technical efficiency that I said under CRS or VRS. We've already said that. That's the one at the top here. And then decomposing that score from the CRS DEA into 2, you get a pure and then the scale. You said that already.
Yes.
The other types. of retention scale, which identify the retention scale that apply at the local level. So note that. The best way to understand and appreciate retention scale, I can use this graph to explain. We said that the technical efficiency under CRS is the VRS score and times the scale efficiency, which means that if I want scale efficiency, I just divide the CRS score by the VRS score. Now, if you check these firms here, I've drawn the constant retention scale graph. That's the one that goes very, very, very straight here. Okay. Now, when you check carefully, you will notice that the VRS is the one that is a curvature one. Some of the firms are on the CRS. Which firms are on the CRS frontier? Which firms, Jerry, are on the CRS frontier? Which firms are on the CRS frontier?
No. Firm B, C, and Q.
I can't hear. You sound so far away.
Firm B, C, and Q.
Okay, there's one more.
And M.
Okay, so those are the ones. Okay, now if you check A, is A CRS or VRS efficient? A.
Doc, can anyone answer?
Yeah, anyone.
Okay, Doc, yes, A is VRS efficient.
A is VRS efficient. Is it CRS efficient?
No.
So it's CRS inefficient. Take note. Okay. Now I can calculate, because it's inefficient, I can calculate, because we know that it's CRS inefficient. Okay, which means that it must be operating under IRS, increasing returns, or DRS, decreasing returns. But which one? What you got to do is to calculate the scale efficiency. Then it will tell you. If you calculate the scale efficiency and it is less than 1, then it is IRS. Now, how do you do that? Remember, this is a CRS frontier here, the one here. Okay. Oh. This is a CRS frontier, and this is a VRS frontier. So I can say LM, that is the distance from the origin in the input side, LM divided by LA. LM. The LM means that I'm doing the CRS, because remember, scale efficiency is given by the technical efficiency under CRS. Under CRS will be LM, that's the CRS, okay? And then for under VRS, it will be LA. So it becomes LM by LA. And LM by LA, if you check it, the value is going to be lower because the distance from LM is lower than the distance from LA. So that means that the gap, which is MA, is what? Who can tell us? The gap, which is MA, is what? Do you know that?
That's a scale efficiency.
Exactly. That is a scale efficiency. You know, that is scale efficiency. If you take B, point B, and you are trying to find the scale efficiency, what would be the scale efficiency for B?
Doc, the scale efficiency for B will be 0 because there's no gap between the CRS and VRS.
Yeah, but it's not 0. So it's going to be what?
Doc, it will be 1.
Exactly. It will be 1. What will be the scale efficiency for C?
Also 1.
Also 1. So you see that both of them are scale efficient. When you are scale efficient, it simply means that your VRS score and your CRS score are the same. It does not necessarily, take note, it does not necessarily mean that they have efficiency score of 1. Okay, you can still, you can have a firm here. Watch what my cursor is. You can have a firm here. The firm is inefficient. But then the locality that is operating is under both CRS and VRS locality. So the firm may have an inefficiency score of, or efficiency score of 0.8. And then that will be the technical efficiency. And then under VRS. And then the technical efficiency under CRS will also be what? 0.8, sir. isn't it?
8, yes.
And so when
Yes.
you divide both of them, you get a scale efficiency score of 1. So I'm saying that it don't have to be efficient to be scale efficient. Do you get a point? This is beautiful.
Yes.
Write it down. You don't have to be efficient to be scale efficient. You don't have to be efficient to be scale efficient. You should be able to explain that graphically. Now, so for all those one, the scale efficiency is going to be 1. Now, when you are scale efficient, then we say that you are producing at the most productive scale size. The most productive scale size. Okay. But now let's look at those that are not. So for DME like this, look at E. Okay. It is not on the VRS frontier, neither is it on the CRS frontier like A. So the way you calculate the scale efficiency score is going to be very, very strange. It's going to be PQ. Okay. PQ divided by PR. But technically, that is not how you would have calculated it, because it's the distance from the origin to the frontier, PQ, divided by the distance from the origin to the FEM, which is PE, isn't it?
Yes.
Yes. But now, so that will be the efficiency score. But that will be efficiency score under what frontier?
Under the CRS.
Under the CRS. Yes, just a second. So the scale efficiency there, let me see. The scale efficiency there will be PQ over PR. Who can explain why it is PQ over PR? Why did it mathematically become that? Yes. Emily.
No, because if you look at where the SC has been defined, that's the one in red, you can see that the PE will cancel itself out.
That's it.
And so you'll be left with the PQ over PR.
But you know that
again.
Okay.
Okay, so the first one, which is for the CRS, will be the PQ over PE. And then VRS will be PE over PR. That one too will still be, but it's going to be divided. You see, the formula is the technical efficiency for CRS divided by that of VRS. So for CRS, you have the PQ over PE. And then for VRS, it would have been PR over PE. And so if you want it to multiply, you have to switch it. And when you switch it, you can just cross the PE out.
Okay, same. Thank you.
Okay. So now we can use this principle, and it's very important because it's not just a matter of telling the reader that, oh, I'm using VRS, or I'm using CRS. You have to understand, you have to be able to break it down for somebody to know the implication of each one of these. It's very important you yourself, you understand the difference between VRS and CRS, as well as the local retention scale. And what we are doing now are the local retention scale, not the industry returns to scale. Okay.
Your doc is muted.
Yeah, Doc, please, you are muted.
Oh my goodness. Okay. I was saying that now we should understand the relationship between the constant and then the variable retention scale, that within the vicinity here, you'll be having IRS, but the IRS is only applying because of VRS technology. The word VRS technology is an industry concept, but the CRS technology is both an industry and then a local concept. Do you guys understand that point? It's very important. The word
So please come again.
the CRS represent an industry concept as well as a local concept. But the VRS The VRS word, the word VRS is only an industry concept. Its local concepts are the IRS, CRS, and DRS. So when I say local, I'm talking about the firm level. So in the firm level, the firm level, we talk about IRS, CRS, DRS, all firm level terminologies. But industry level terminology, you are talking about CRS and VRS. That is why you know that CRS is both an industry and a firm level terminology. Does that make sense?
Yes, Doc.
Okay. So now let's move on to the next. So if we estimate the VRS local returns to scale for H, you see, I said VRS, but I'm talking about local returns to scale for H. If you check it for H here, you will see that H will hit both the CRS section and then it will also hit this one, but depending on the orientation, isn't it? If you are doing an input orientation, you go here, so it becomes IRS. If you are doing an output orientation, you go up here, so it becomes a DRS. So H is exhibiting both IRS and DRS depending on the orientation. So it means that the orientation matters. Orientation matters. That is why you can't pick both orientation. If you pick both orientation, then you have to be clear where the thing is operating. But of course, if you pick both orientation too, then you're not going to do a radial measure, isn't it? You're not going to do a proportional measurement. So this point is very, very important. So if increasing returns holds at the Pareto efficient production point, then if you raise the input levels by a small percentage, that's the increasing return. That's the definition of increasing return. If you increase the input by a small percentage, the output will increase big. That is increasing returns. Unlike the decreasing, where if you increase this one with a small or big percentage, the output will increase, but it will increase by less. Therefore, local returns to scale determination at the firm level is very important for managerial decision making. For example, if a firm is too big and another firm is too small, the too big guy is said to be operating at decreasing returns to scale. It means it's too big, so it has to reduce. And then the too small guy is operating at increasing returns, so it has to what? It has to increase. So you, as an analyst, you would now suggest to the company to combine the two. That's the measures and acquisition that comes into the picture. So a DMU operating at an increasing return must raise, because it's too small, it must raise the size, the scale size, because it's the extra inputs may be more compensated for by the rise in the output. And that is what Banker calls the optimal scale size, the most productive scale size. So this returns to scale concept is a very important. And we know that scale efficiency measurement, we calculated it how it is, you see, before you can talk about scale efficiency, you must calculate both CRS and VRS. Yeah. So even if you go and choose that, oh, this industry is exhibiting blah, 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 and let's say it's VRS, you can't talk about scale except if you also calculate the other one. If you calculate the other one, then you can now be able to, conclude that it is exhibiting, you can have an industry where your industry is VRS, but if you want to talk about scale efficiency, you got to go ahead and do the CRS calculation, because the two is needed to find the scale. So this is an R code for estimating what we did. So the data set we have, I called it Farm 1. This is the number of inputs is 2, the number of output is 1. I just call it this name. If you load the data, that's same 5DMU's data. You solve for the orientation. As you can see, the orientation is input orientation, because there are 2 inputs here. The returns to scale, I'm assuming CRS. Okay, I'm assuming returns to scale to be CRS. And then I estimate the efficiency score called R. this will show the efficiency score. But if I type RTS of the score, RTS, retention scale of the score, it will give you all the retention scale that you need. Okay. And I think in this one, because the firms are so small, I think all of them were operating at the same retention scale, increasing retention scale. Because remember, they are all in the input-oriented state. But if they were in both input, you see, if you have this, both input and output oriented, that is when the retention scale become apparent. That is when you know that IRS is here, DRS is here, CRS is here, and all of that. So this one, unfortunately, when you go and check, you see that they are all IRS. Or maybe they are even all CRS. No, DRS. Because we didn't draw it in an input-output case. So I have this assignment that I want you to execute. I want you to do it based on all that we've done today and before. Here, the data set did not show. The data set did not show. So I'll send you the new one that is showing the data set. I can't believe that the data set did not show. Okay. But hold on, let me just. What I'm going to do is I'm still going to I'll put it in the slide for you, but right now I'm just going to take a picture of it and post it in the page for you. Okay. It's about a banking. Please, somebody should say hi and let me see. I want to see something. Say hi on the page. Let me see something. Okay. So I've just posted the data sets on the page you might see. But basically, it's a simple data set. But check carefully, and you will know, is it input-oriented or output-oriented? Well, from the question, you know, right? So this is an
Yes.
output-oriented one. I didn't want to give you another input-oriented for you to come and bluff. So you have to formulate an output-oriented model under the VRS to assess the efficiency of the history department. Okay, you will see the departments are in the pictures. How would your model change under CRS? What does each constraint mean? You have to explain it. Using a good skill, draw the production possibility set, identify the efficient frontier. You have to do all of this and submit. This is an assignment that I need you to. Is this your first assignment or second?
Like the second.
This is a second. Good.
Yes.
Pinpoint on the
Please, the first assignment, should it be hard copy or we should send you the
hard
soft
copy.
copy?
Hard copy.
Okay.
Yeah.
You'll print and send.
Pinpoint on the graph using the PPS. What is approximate efficiency score for history? If it is inefficient, what are the PS? Many of the departments achieve efficiency score of 100. Why is that so? Okay. Then you have the next one. The efficiency of 5 petrol stations. That one to the data is here. Can't believe that one to didn't show. Oh, you don't need that one. Why is then? No, you don't need that one. Wait. I think the one I even gave you is different. The one I gave you is not a history one.
Yeah, the one you gave is banks
Yes, hold on.
from A to G.
This is petrol stations. No, not this one too. So the one I gave you is banks, right?
Yes, Doc.
I need to give you all of these. Why can't I see it? All right. So what I will do is I'll do a Word document of all of them because you're going to answer all of them. I'll do a Word document of all of them. Then you submit this one. It is a kind of 3 different assignments that you're going to be doing. But because the first one is 1, it starts here as 2. You're going to draw
Okay.
some, you're going to do R for some and all of that. So just take note of that. All right, that's it for today. If there's no question, enjoy the rest of your day. But if you have a question, you may ask.